What's up, Marlet fam? My name is Russell, and today we'll be talking about the most important evolutions in aerospace history and in the industry, baby. I told you long ago how to roll. All right, so to top out our list, on number one, we're going to be talking about the hot air balloon at number 15. Here we go.
Imagine floating thousands of feet above the ground with no engine, no wings, and almost no sound. Just hot air keeping you in the sky. Today, I'm going to talk about one of the earliest and most important aerospace engineering achievements, the hot air balloon. Hot air balloons were the first successful human flight in history and laid the foundation for modern aviation and aerospace engineering. In this video, I will explain when and where hot air balloons were invented, who created them, how they work, what scientific and engineering advancements made them possible, what was happening in the world at the time, and how this invention affected future aerospace technology. The first successful hot air balloon flight took place on June 4, 1783 in Annonay, France. This achievement is considered the first public demonstration of human flight, even though the first flight did not carry people. The invention originated in France during a period known as the Age of Enlightenment, when science, experimentation, and engineering were rapidly advancing. The hot air balloon was invented by Joseph Michel Montgolfier and Jacques Etienne Montgolfier, known as the Montgolfier brothers. They were paper manufacturers, not pilots or engineers in the modern sense, but they were careful observers and experimenters. Joseph noticed that heated air caused lightweight materials to rise, and together, both the brothers experimented with fabric and paper balloons filled with hot air from fire. This one is Jacques Etienne Montgolfier, and this one is Joseph Michel Montgolfier. This is one of the sketches of their early balloon designs. The Montgolfier balloon worked using a basic scientific principle called buoyancy. When air is heated, it becomes less dense than the cooler air around it. This causes the hot air to rise. The balloon envelope, made from cloth and paper, trapped the hot air inside. As the air heated up, the entire balloon lifted off the ground. On September 19, 1783, the Montgolfier brothers conducted a famous experiment by sending a sheep, a duck, and a rooster into the air in front of King Louis XVI. On November 21, 1783, the first human passengers, Jean-Francis Pilatre de Rozier and Francis Laurent d'Alandres, successfully flew for about 25 minutes over Paris. The hot air balloon flights received massive media attention. Newspapers across Europe reported on the experiments and large crowds gathered to watch the launches. People viewed ballooning as magical and revolutionary. It captured the imagination of scientists, engineers, and the general public, proving that human flight was possible. Several scientific and engineering advancements made the hot air balloon possible. First, scientists had begun to understand air pressure, density, and temperature. Second, improvements in materials such as lightweight fabrics and paper allowed balloons to be large but not too heavy. Third, controlled fire and combustion made it possible to continuously heat the air during flight. These developments combined science, technology, and engineering into one successful aerospace design. The hot air balloon had a huge impact on the future of aerospace engineering. It proved that humans could fly, inspiring inventors to experiment with airships, gliders, and eventually airplanes. Balloons were later used for weather research, military observation, and atmospheric science. Today, modern hot air balloons use advanced materials, propane burners, and precise engineering, but they still rely on the same basic principles discovered in 1783. In conclusion, the hot air balloon was one of the most important aerospace achievements in history. Created by the Montgolfier brothers in 1783, it combined science, engineering, and creativity to achieve the first human flight. This invention not only changed how people viewed the sky, but it also paved the way for modern aviation and space exploration. Even today, hot air balloons remind us that great engineering begins with curiosity, experimentation, and imagination.
Thank you for that. Now, number 14, we'll be talking about cabin pressurization. All right, and here it is.
When cabin pressurization fails.
What was that?
Pressure drop! Pull down a mask!
Oh my god, okay.
Oh, look here, put this on, press it tight.
I've got it.
Normally, that's it.
What is cabin pressurization? Cabin pressurization is the system that keeps the air inside an aircraft at a safe, comfortable pressure even when flying at high altitudes. It works by taking compressed air from the engines and rerouting it into the cabin, allowing planes to fly higher, improve fuel efficiency, and reduce passenger discomfort. Without it, the thin air above 30,000 feet would make breathing very difficult, and that's where the oxygen masks come in as a backup. Before cabin pressurization was created, people had to wear oxygen masks whenever they were flying at higher altitudes, or they'd risk getting symptoms like hypoxia, which was very inconvenient for traveling. The first successful flight using cabin pressurization was by the U.S. Army way back in June 1921, but it wasn't until 1938 that passengers could experience it on a commercial airliner. The Boeing 307 Stratoliner was the first to feature it. The idea itself had been floating around since around the 1920s and 1930s, with early concepts being developed by engineers experimenting with high-altitude flight. Some of the key figures include Jean Roche, who came up with some of the earliest designs of it, and Harold Harris, who ran the first successful experiments. Major Carl Green and John Younger are credited with the first practical implementation of cabin pressurization, with Garrett AI Research later developing the mass-produced system that went into the B-29 bomber, making high-altitude pressurized flight a reality. The introduction of the first pressurized airliners, like the Boeing 307 Stratoliner, was considered headline news and a significant technological leap in the aviation industry at the time. Media coverage from the era highlighted the unprecedented comfort, speed, and luxury of flying above weather disturbances, which revolutionized the idea of commercial air travel. At the time of creation, the world was facing pre-World War II tensions that were rising in Europe. It was a difficult time economically due to the Great Depression that just happened, but the push for technological advancement in aviation continued strong. Some advancements that made cabin pressurization possible include stronger aluminum alloys, creating a sealed fuselage, superchargers that produced the compressed air, better manufacturing techniques, which included the riveted monocoque fuselages, and early environmental control systems, which included temperature and pressure regulation, which all together made a safe, airtight cabin possible. To help me talk about how cabin pressurization affected the future, I have my friend Antonio here to do an interpretive dance showing how people were very excited about having more efficient and quicker travel. Cabin pressurization completely changed the future of aviation. Before, aircrafts were limited to lower altitudes where flights were slower, less efficient, and more affected by weather, causing lots more turbulence. With pressurized cabins, however, planes could fly much higher above the turbulence and storms, making flights smoother, faster, and safer. This advancement also made long-distance transcontinental air travel possible because passengers and crews could survive comfortably at high altitudes for extended periods of time. As a result, aircraft designers were able to create larger, faster, and more advanced airplanes. Cabin pressurization also influenced military aviation, allowing bombers and reconnaissance aircraft to operate at higher altitudes where they were harder to detect and find. Overall, this single advancement of cabin pressurization laid the foundation for modern commercial jet travel and many of the aerospace technologies that we rely on today. Cabin pressurization changed how high, how far, and how comfortably we can fly. It may not be something passengers think about when they're aboard a plane, but it's one of the most important engineering advancements in aviation history. It transformed flying from a dangerous, uncomfortable experience into a safe, efficient, and global form of transportation.
That was very awesome. Next on our list, at number 13, is going to be the radar. Take it away.
Hey guys, Eden here, and welcome to my 1.1.1 presentation on radars. Now, Eden, I hear you asking, what even are these radar thingamabobs, and why should I care about them? Now that's a great question. Let me consult my book. This was $30. Anyways, radar stands for radio, detection, and ranging. Radars are used in a lot of people's everyday lives, from their use in planes, cars, ships, military and defense, and even weather formation. Now, radars work by sending out radio waves and then analyzing the signals that bounce back after hitting an object like this one. By studying these reflected signals, the radars are able to determine this object's direction, distance, and speed, whether the object is another aircraft, ship, car, or even terrain. Now that might sound a little confusing, so that's why our good friend Mr. Aiden Dawson is here as a willing test participant. Say hi, Aiden.
Hi!
Let's say Aiden is trying to find his car, but he can't see at all because he's blind. If Aiden were to yell out radio waves using his signature catchphrase,
Life gives you lemons.
those waves would travel outward, hit the car, and bounce back to him. By listening for where the echo comes back the strongest, Aiden can figure out the direction of the car. That's how radar determines where something is. Now, direction is useful, but I'd also like to know how far away the car is. Luckily for Aiden, radio waves travel at the speed of light. So all Aiden has to do is measure how long it takes for the signal to go out, hit the car, and return. Multiplying the speed of light by that time, then dividing by 2, because the wave travels to the object and back, and then baba gaboosh, you got your distance. But what if the car is moving? That's where the Doppler effect comes in, or as I like to call it, the disappointing endeavor, because I spent way too much time trying to figure out what this thing is. To put it simply, when an object moves towards you, the waves come back slightly compressed, while when it moves away, they stretch out. That change lets radars detect if an object is moving towards or away from you, and based on how compressed or stretched out they are, how fast as well. Aircraft use these same radar principles to maintain their daily systems and operations as well. For example, they help air traffic control track where plane locations are to maintain safe separation and ensure no collisions. They also help detect weather to see if they need to make any changes to their course, as well as warn pilots when terrain is too close, like in those automated pull-up messages.
Too low, terrain, pull up. Too low, terrain, pull up.
Alright, back at the whiteboard. The first practical radar system was developed in 1935 by a man named Robert Watson Watt and his team in the UK. They developed a ground-based radar system called the Chain Home, and it was mainly developed because of the rising tensions between Germany and the UK before World War II. Now you might think, great, slap that thing on a plane and call it a day. The thing is 360 feet tall. That is not going to be slapped on a plane. You would have think it would take 20, 30 years to shrink it down to that size and be able to put it on an aircraft. It took 5 years. So, by 1940, British aircraft like the Bristol Blenheim or night fighters were equipped with the first airborne radar that allowed them to intercept and shoot down German planes at night, which was effectively impossible before the invention of radar, during the time when Germany and UK were in full-on war during World War II. Now, media coverage of radar was practically non-existent during the war, since most of the documents were classified. However, after the war in 1945, it was recognized by a bunch of newspaper outlets as one of the key technologies that helped secure the Allied victory. Now, the development of radars was only possible because the previous scientists and engineers knew technologies and theorems. The big 3 examples of this I can find is the development of the electromagnetic wave theory, as without it, nobody would have known what a radio wave even was. The development of vacuum tubes and magnetrons, as they were crucial in order to generate strong signals, as well as the development of antennas and signal processing, as they were needed to interpret the returned waves. Radar also continues to shape the future by making things more safe, as radar can normally see things that we cannot. For example, it allowed for air traffic control systems to be expanded on a major level. It allows for onboard weather radar, autopilot and collision avoidance technology, as well as satellite tracking and space exploration. So even though it operates behind the scenes, it plays a major role in everyday life.
Wow, that was really good. Bro was cooking. Let bro cook. Let him cook.
I don't know.
Anyways, number what are we at? Number 12 will be the jet engine.
I'm Xavier, and this video is about jet engines. In this low-budget production, I hope to explain to you the underlying principles and aspects of how a jet engine works. And maybe, just maybe, you might even learn something. By the end of this video, I hope to have convinced you that the jet engine is just as simple and familiar as the engine found in the car in your driveway, the lawnmower in your shed, or even the racing lawnmower at your buddy's house. Hell yeah. But if you don't know what all these have in common, don't worry, I got you. A 4-stroke, also referred to as a 4-cycle engine, has 4 cycles: the intake, the compression, the combustion, and the exhaust. A jet engine has the same 4 stages/cycles, but instead of using a piston to execute them, it uses a series of impellers or turbines to carry this out. This achieves continuous combustion because as exhaust air continues to hit these rear turbines, the turbines spin the impeller, which brings in more air, and it just keeps going over and over. Instead of 4 distinct stages like a 4-stroke engine, the only difference is this is continuous. There is no distinct 4 moments or 4 times where each stage is carried out. They're all happening at the same time. That's the only real difference between this and the 4-stroke engine. In today's modern age, there are 2 main types of jet engines. The first is the high bypass jet engine. You're probably most familiar with it because it's the same type of engine used on modern jet airliners. It gets its name because the first fan in the series of axial fans is ginormous and diverts nearly 80% of the air around the actual engine itself. This first fan is responsible for producing most of the aircraft's actual thrust, and the remaining 20% of the air that the first fan moves is diverted into the engine, whose exhaust gases are used primarily to spin the huge fan. The biggest problem, however, with the high bypass jet engine is that while the large first fan allows the engine to be extremely efficient, it also produces lots of drag at high speeds, making it far less ideal for those kinds of applications. That brings us into our second kind of engine, which is the low bypass jet engine. It's specifically made for high-speed applications such as fighter planes and ditches the large first fan. This makes it much more aerodynamic at speed and also means that it produces most of its thrust primarily just through its exhaust gases. While this engine is far less efficient than the high bypass jet engine, there is a way to boost efficiency through the use of an afterburner. This still doesn't bring it anywhere near the efficiency of a high bypass jet engine, however, you still do gain some of it back. It works by utilizing the low bypass jet engine's extremely hot exhaust gases to inject fuel post-exhaust to allow for a second combustion stage. This brings us to the jet engine that I designed. In order to explain this, we have to leave the modern age and go back to the ye olde days of the centrifugally compressed jet engine. Unlike modern axially compressed jet engines, centrifugally compressed jet engines utilize an impeller to bring air in and fling it outward. I've been working on this model on and off, mostly last semester, because I really wanted to try to make one. Obviously that hasn't happened yet. It's missing a lot of things, one of which is a way to actually start the ignition, whether that be a spark plug or whatever. There's currently not one modeled. The second big thing is a way to actually start the engine, which I'll discuss later in the video of how jet engines are usually started. I chose to 3D print this model so that I could illustrate the path of the airflow and how everything's working together. So first we start on the intake side, where the impeller flings and consequently compresses the air into the first channel. This air then goes into the divergence pathway, where it will hopefully create a Venturi effect to act as like a carburetor to suck fuel in. Then this fuel will go and follow this channel and be dispersed into the combustion chamber. Then combustion happens in the combustion chamber. Exhaust gases flow backwards. This high-speed exhaust gas hits these turbines, spinning the shaft and the connected impeller as one. This is why there's continuous combustion. The air continues to be intaked, fuel continues to be injected, combustion continues to happen, and the turbines continue to spin, and so on and so forth. One of the many benefits of a centrifugally compressed jet engine, especially at this scale, is the part-to-compression ratio. This means that this type of engine requires far less parts to create the adequate compression for combustion. A axially compressed engine requires lots of turbines, all connected along the same axis and spun around the same shaft. This is very efficient because all of the air keeps getting pushed backwards axially rather than like an impeller being flung out to the side. A axial compressor just flings it backward. So there's way less resistance on an axial compressor. Now, as you may be wondering, one of the, if not the hardest part of all jet engines is how do you start it? Once the combustion is started, it's easy. It continues on its own. However, starting it is another story. This is done primarily through using a motor that's isolated away from all the moving parts and hot gases. In this case, connected by a series of bevel gears down to a shaft that has a clutch attached to it, which is then attached to the motor. The clutch here is one of, if not the most critical parts, because once the engine is started, you don't want all the torque and rotational energy of the motor coming back through the gears and into the motor. Well, that's all for me. I hope you learned something, and on to the next guy.
Hell yeah. This is my turbine. I may not like it, but this is
Yeah. In this low-budget production, I hope to explain... Run it back. Forgot what I was going to say.
What?
I should start with...
Turbo!
I don't know. Yeah, pretty much. That's the thing.
Let me tell you something right now, man. I got done rolled this thing 3 times. These lights right here, factory equipped. Okay. You can't handle the heat on this thing when you're on it, alright?
Is the sun in my face?
Wow, that video was really good. I love the part where he asked if the sun's in his eyes. What'd you think, young Russell? Oh, I thought that video was really good. I love the part where they're on the tractor. Me too, young Russell. And with at number 11, we have supersonic flight. Yay. Whoa! I'm flying so fast! Oh my god, was that over there? Is that Mr. Marlette's class? I swoop in! Whoosh! Hey guys, I'm Russell Donofrio, and today I'll be talking about supersonic flight. Probably wondering what I'm going to talk about. Well, today I'm going to talk about the history, the people, and the advancements supersonic flight had on the aerospace industry. Okay, guys, here we go! Supersonic flight is one of the most important achievements in aerospace history, flying faster than the speed of sound, which is about 767 miles per hour, and was once thought to be impossible. Over time, the advances in technology, science, engineering proved that supersonic flight could be achieved and controlled, changing aviation forever. On October 1947, pilot Chuck Yeager became the first person to fly faster than the speed of sound. And the speed of sound, he piloted the Bell X-1, a rocket-powered aircraft designed to handle extreme speeds. The plane was released from the B-229 bomber over the Mojave Desert and reached Mach 1.06. At the time, many believed the sound barrier would cause aircraft lose control or break apart. It didn't. Yeager's successful flight proved those fears were wrong and marked the beginning of a supersonic era. This achievement took place shortly after World War II, during the early Cold War, when nations were heavily investing in faster and more advanced military aircraft. More than 20 years later, supersonic flight entered commercial aviation with the Concorde. Not the city. Whoa, off control there. First flown in 1969 and entering passenger service in 1976. Concorde was developed by France and the United Kingdom. The aircraft could fly at Mach 2 and cross the Atlantic Ocean in just over 3 hours. Concorde used delta wings, powerful afterburning engines, and heat-resistant materials to withstand high-speed temperatures. During the space race, Concorde became a symbol of technological progress in international cooperation. Although retired in 2003 due to high operating costs and environmental concerns, Concorde proved that supersonic master travel was possible. Sorry, I'm still staring. In 2003, supersonic flight reached another milestone with Spaceship One. The aircraft became the first privately funded piloted vehicle to exceed the speed of sound. Built by scaled composites, Spaceship One showed that advancements in aerospace innovation was no longer limited to governments. Its success helped inspire the modern commercial aerospace and private spaceflight industries. Supersonic technology continues to advance today. In January 2025, Boom Supersonic's XB-1 aircraft broke the sound barrier, when the first independently developed the civilian jet to do so. The XB-1 uses modern aerodynamic, lightweight composite materials and advanced avionics. The milestone represents a renewed effort to bring supersonic travel back in a more efficient and environmentally responsible way. Another challenge in a supersonic flight has been the sonic boom. When an aircraft exceeds the speed of sound, it creates a long, loud sonic shockwave that can be disrupted on the ground. NASA's X-59 aircraft was designed to reduce this boom into a quieter sound. Using advanced shaping and engineering, the X-59 could allow supersonic flight over land and change current aviation regulations. From the first supersonic flight in 1947 to modern research aircraft and private companies, supersonic flight has pushed the boundaries of science, technology, and engineering. Each advancement built upon early discoveries and continues to shape the future of aerospace innovation. Sorry, guys, a little manic, because I'm flying an airplane. Uh-oh. Wait, what year is it? And where am I? Uh-oh. Hey, guys, me, Russell. I've been told my joke was offensive, and I've been to prison for it, on top of crimes against humanity for all the attempts I made on the freshmen at Indialand High School. So, I'm gonna show you some media coverage of supersonic flight. I'm going to be never released. I'm unable to get bond. I miss my family. Enjoy my video. Yeah.
In the room we are on card 1. We've just received takeoff checks and takeoff briefs. We need the control room full. This is going to be a verbal from the leads. Starting over here with Zeus.
Zeus, go for takeoff.
UCS, go.
Fuel is go. Prop go.
BMS go.
Air data go.
FQ go.
Avionics go.
Flutter go.
Hydro go.
Flags go.
Loads go. SR go.
TD, go.
Control copies all. X-59 control is go for takeoff.
All right. Thank you guys for watching. I'm gonna have to go get executed now. Safe travels, and thank you for listening. Big Russ out. End video. Hey guys, Russell here. I'm still in prison. I was in a bit. Now we're doing number 10. Here it is.
Planes. More specifically, aerial refueling. The system and process that people call the lifeblood of aviation these days. Imagine flying for days without landing, crossing oceans and continents on a single mission. Today, that's routine for military aircraft thanks to aerial refueling. The first systematic, successful aerial refueling is usually dated back to 1923, when 2 U.S. Army Air Service biplanes flew over San Diego, California, and managed to funnel fuel from one plane to another. This achievement came only a few years after World War I, when the nation was starting to enter the roaring 20s. From a STEM perspective, this first refueling was amazing, depending on basic fluid mechanics as it was simple to reproduce. Here we have the probe and drogue system, mostly used by the US Navy and other NATO allies, and we'll see it in action right here. So the drogue system that we have with the US Navy and the NATO allies is a very freeform system, freeform in the way that the drogue coming from the tanker is very flexible, very fluid, and genuinely it is on the pilot's side where he has to kind of maneuver and move into the place where they need to be to connect their receiver into the drogue. And we'll see contact in just a few seconds here. There we go. Next after that, this system called the boom system is used by the US Air Force. And it's much more rigid, and we'll see here in just a second. We have a B-52 here coming up and trying to refuel. Now, the boom system used by the US Air Force is much more rigid, and there's actually a boom operator inside of the tanker adjusting and moving the boom to make sure that they can slot it into the B-52's receptacle that you can see right on the top there. So it's very much kind of, I would say, a reverse situation in how these pilots and how these personnel come around approaching and how they approach actually connecting the planes and getting the fuel through. From the 1930s onwards, it really went from a novel technology to something much more strategic. By the 1930s, Cobham's Flight Refueling Ltd. determined that more advanced loop tow systems were much more efficient and was a major engineering upgrade. And as the world moved towards World War II, long-range bombers and maritime patrol aircraft became central to strategy, and refueling offered a way to extend their reach without building entirely new airfields. The geopolitical pressure of global war accelerated STEM development, navigation, radio communication, and engine efficiency, all of which made aerial refueling safer and more practical. These advancements directly influenced later Cold War thinking. If aircraft could refuel in the air, they could potentially strike targets or patrol borders anywhere on the planet. This idea set the stage for modern concepts of global reach and power projection that still shape aerospace designs today. And when you were moving early in the 1930s, 1940s, it was much more of a novel technology. I can't emphasize that enough. People were actually using aerial refueling as a stunt, and there were quite a few records set, 37 hours, so and such. Now, as you move later into history, more towards the modern day, modern systems start to appear. So our modern systems we have in today with the probe and drogue as well as the boom system came around 1948 when the US Air Force started using their long-range strategic operations. And they gave a really high priority to tanking technology just due to the power projection it could provide. Around this time, flight refueling and Cobham developed what was to become the probe and drogue system, with operational testing starting around 1955. Shortly afterward, the US Air Force and Boeing advanced and created the flying boom system, and that's where we see the separation in the modern day today. Modern tankers such as the KC-46 Pegasus and A330 MRTT still use the boom hose and drogue systems, but now integrate higher technology, digital cameras, and high definition visuals, and to help with visualizing the situation outside of the cockpit for the operators inside. That's the history and the future of the aerial refueling industry. Thank you so much for listening.
And thank you for Nook for that awesome video. It was I think it's very bold of you to do a shorter video than was required. But I think it was very, very. I never seen someone pull it off like you could, Nook. Anyways, number 9 is.
I'm probably not even going to crop this out because I'm too lazy. Hi, my name is Christian, and today we will be talking about the helicopter. If you can hear my cat purring, that's not my issue. Anyway, helicopters are one of the most recognizable aircrafts in the world, as they are used for everything from military missions to medical rescues. What makes them so interesting is that they can hover, fly sideways, and take off vertically. These are things aircrafts can't do. Today we'll be going into a deep dive in the history and evolution of helicopters, explain their design and how they work, and briefly cover why they were researched. Thank you. Alright, let's do this again because my mic was off. I'm an intelligent human being. Let's do this. The idea of vertical flight has been around for thousands of years. It started in the 1400s when Leonardo da Vinci drew his famous aerial screw, and even though it was never built, it showed that people were already thinking about how spinning surfaces could lift a machine off the ground. The real challenge came centuries later when inventors tried to turn these ideas into actual flying machines during the late 1800s and early 1900s. Inventors experimented with steam and gasoline engines, but most of the helicopters are unstable or unsafe. A major breakthrough happened in the 1930s when Igor Skavorsky developed the VS-300, the first practical modern helicopter. His design introduced a single main rotor combined with a tail rotor, which solved the problem of uncontrollable spinning. The layout is still used today in most modern helicopters. By World War II, helicopters were being used for reconnaissance and rescue. After the war, helicopter technology rapidly improved, leading to a widespread civilian and military use. Once the basic designs were proven to work, engineers focused on improving control, safety, and power. Early helicopters were difficult to fly, requiring constant correction from pilots, and struggled to even get off the ground. The development of cylindrical and collective controls allowed pilots to control direction and altitude more smoothly. Stronger engines made it possible for helicopters to carry heavier loads, while improved materials made them lighter and more durable. By the mid-20th century, helicopters were reliable enough for combat, rescue missions, and transportation. Helicopters used turbine engines, digital flight systems, and advanced materials like carbon fiber, making them far more compatible than earlier models. Helicopters are uniquely designed compared to aircrafts. The most important part is the main rotor, which provides lift. The rotor blades are designed like airplane wings, and as they spin, they create lift by changing air pressure. The tail rotor counteracts torque created by the main rotor. Without it, helicopters would spin uncontrollably. Some helicopters use alternative systems like dual rotors to solve this problem differently. Another critical component is the swash plate, which allows the pilot to change the angle of the rotor blades while they're spinning. This lets the pilot move forward, backwards, sideways, or even hover in place. The fuselage holds cockpit, passengers, cargo, internal systems, and a lot of others. Helicopters usually have skids or wheels, allowing them to land on uneven surfaces. Every part of a helicopter is carefully designed or balanced to lift, control, and stability. But because of helicopter designs, this makes them highly vulnerable and highly easily to be damaged or broken. Whether in military, where even a single stray gun round can break it, or even in just normal situations like a rainstorm or a sandstorm, helicopters can be broken very easily. CH-47 Chinook. The Chinook is known for its tandem rotor design, meaning it has two large rotors, one in the front and one in the back. This design eliminates the need for a tail rotor and allows the Chinook to lift extremely heavy loads. It has been widely used by the military for transporting troops, vehicles, supplies, but it's also been used in medical situations to help reach people in tough places, like atop of mountains and in other hiking areas or in valleys and whatnot. Another important helicopter is a UH-60 Blackhawk, which is used for troop transportation, medical evacuation, and special operations. It is known for being fast, durable, and versatile. A major role in civilian aviation is the Bell 206 Jet Ranger, becoming popular for its training, news reporting, and tourism. Each of these helicopters has helped prove how adaptable helicopter technology can be depending on its design and purpose.
Wow, that video was so awesome. The next video will be even more awesomer. Cause we're going to number 7. Number 8. Oh no, I forgot.
Hello YouTube, Daniel here, and I am going to be covering the topic of tracking missiles. And I'm going to be talking about the first ever tracking missile, which is called the ASMN-2 BAT, which was created by the U.S. in 1945 of April during World War II to do naval battle against ships. So it was created by multiple U.S. organizations such as the National Bureau of Standards, Navy's Bureau of Ordnance, Massachusetts Institute of Technology, and Bell Telephone Laboratories. And there are some individuals that were specifically credited and mentioned in the past, and they are Hugh Latimer Dryden, Sarkis Tadigian Charles Register, and Ladia S. Adams. So, this missile was the first automated target-seeking smart missile, and how it worked was there was a giant plane, and it was just like basically a bomb with wings. So they would drop the bomb, and it would use its radar to sense if there were any ships in the area, and then it would control the wings, and it would glide towards the ship and destroy it. So I do have some information back here because I can't remember all this. Okay, so the advancements in science and technology that allowed this. So it was possible in the advancements in radar homing, autopilot systems, and aerodynamics. The radar homing was possible because of the systems utilizing cavity magnetron to send radar pulses which would bounce off a target and send back to a parabolic reflector. The autopilot was possible because the radar was linked to it and the servo motor system which controlled the elevens. I think that's how you pronounce it, which are the little wing part of the bomb. And this affected future aerospace advancement and achievement because it brought more attention to radar homing, so it would be more improved, and there would be a higher guarantee of hitting the target, because back then they would just let it go and there wasn't always a 100% chance that it hits the actual target. So they also added a safety mechanism where there was a timer and the bomb would be set off at a certain amount of time if it didn't hit anything. So it also brought the foundation for anti-ship missiles, because this was one of the first of its kind, and it became a standard part of naval aviation today. And it is a direct ancestor of a more modern homing missile, which is the U.S. Navy's Harpoon anti-ship missile, and it also influenced many air-to-air missiles, which are used in the Air Force, that's what it's called. So I'm just going to show you a quick video I created showcasing the ASMN-2 BAT. This showcases the radar ability and the tracking sequence it had. So please enjoy the video. I hope you like that little demonstration. As you could see in the little short video, that the tennis ball acted as the radar system and the refrigerator acted as the ship. So even though the normal radar is a full 360 degrees, we couldn't quite do that. So we just implemented the tennis ball as being a single beam, and the showcases where like the tennis ball was bouncing on a bunch of objects, that would showcase all the objects on the radar that are not the ship. So that kind of demonstrates that. Also, I'm going to talk about a few other advancements that were made because of the ASMN2 bat. So for starters, its design, its like bat wing design, was contributed to the development of low observable aircraft like the F-117 Nighthawk and the B-21 Raider. So the production of it influenced like most stealth technology today. I just want to quickly mention that, but that's the video. On to the next person.
All right, that was number 8. I like the part where the missile. Number 7 coming up. I like that one.
In 1898, Nikola Tesla demonstrated his new invention at Madison Square Garden in New York City. His showcase, the first remote-controlled vehicle, was a roughly 4.5-foot-long radio-controlled boat. While his invention was technically a success, it failed commercially, and many investors believed his invention was purely for theatrics. But the boat wasn't just theater magic. It was a huge advancement in radio technology. He hid a controller with a transmitter in his coat pocket and put a receiver, servos, and battery in the boat. How radio control works is, the transmitter in the controller sends your inputs at the speed of light to the receiver in the vehicle, which then sends electrical signals to the servos and ESC to move the control surfaces and motors in the vehicle. Before the start of the First World War, aviation was still in its infancy. Early aircraft relied entirely on mechanical linkages such as cables, pulleys, and rods that connected directly to the pilot's controls. And while effective, these linkages limited the aircraft's capabilities due to needing a physical connection to the pilot's controls and the plane's control surfaces. Near the closing stages of World War I, the militaries of the Triple Entente began experimenting with unmanned and remotely guided aircraft. One example, by the United Kingdom, is the Kettering Bug. This unmanned aerial torpedo, designed by Charles F. Kettering, was designed to fly a preset distance and then crash into its target. While its technology was revolutionary for the time, flying using gyroscopes and pre-coded electrical signals to actuate pneumatic controls, it never saw combat due to being introduced too late. During the interwar period, more advancements of radio-controlled aircraft were made. The most notable mention is the invention of the radio-controlled aerial drone invented by Walter Reiter. This invention by Reiter, called the Radioplane OQ-2, bought and later renamed RP-4, was the first mass-produced UAV. In 1941, it was bought by both the U.S. Army and Navy for use as aerial target practice. This target drone proved that remotely controlled aircraft had a lot of potential. During World War II, remote control technology made even more notable advances. In 1943, the Italian battleship Roma was sailing to Malta to surrender to the Allies. Whilst going through the Strait of Bonifacio, the Italian task force was attacked suddenly by the German Luftwaffe and struck directly by a Fritz X guided bomb. The Fritz X was a heavy armor-piercing bomb with radio-controlled tailfins. These radio-controlled tailfins allowed the bombardier to steer the bomb directly into its target. This attack notes the first time a capital warship was sunk by a guided weapon. In 1944, the German Luftwaffe put into service the V-1 flying bomb. The V-1 used early autopilot systems. They had gyroscopes to control the pitch and yaw, a compass to keep heading, and barometers to determine altitude. Some V-1s were fitted with radio controls to improve accuracy. All these devices did help the V-1 reach its target, but the V-1 only had an accuracy of at best 7 miles, which means it was better as a terror weapon than a device of actual strategic importance. The Cold War marked a major turning point in aircraft mechanics and design. Aircraft became more streamlined, they were more complex, and traditional mechanical controls exceeded their limits. The supersonic flight design caused issues of low-speed instability, and at higher speeds caused high forces on the control surfaces. Fly-by-wire fixes the issues had with traditional linkages. It converts the pilot's inputs into signals processed by the airplane's computer to precisely move the plane's control surfaces. This technology saves on weight, mechanical complexity, and reduces the amount of force the pilot has to exert to fly the aircraft. While technically invented in the 1930s by the Soviets, fly-by-wire didn't see widespread use until the 1960s. We can see this technology used in military service by the F-8 Crusader and F-16. Another major advancement came with the exploration of space. Satellites, of course, could not have physical connection to their operators on the ground, so all control depended on radio telecommand systems. The Apollo program relied on the astronauts to fly the spacecraft to the moon, and with spaceflight needing to be super precise, the engineers decided that the craft would primarily use fly-by-wire technology with a manual backup for safety. In the 1970s, fly-by-wire entered commercial aviation. The Concorde. Along with being the first commercial plane to include fly-by-wire, it was also supersonic. The next aircraft with fly-by-wire arrived in the 1980s, the Airbus A320. This time around, it had full fly-by-wire, which includes the flaps and spoilers instead of just the main control surfaces of rudder, elevator, and aileron. In the 1990s and 2000s, remote control and fly-by-wire made major advancements with advances in GPS and digital communications. Unmanned aerial vehicles like the MQ-1 Predator could be flown remotely from halfway around the world with real-time video from satellite links. Was started in the late 1800s as a small radio-controlled toy, has transformed into a field where computers and data links and automation are central. No, remote control and fly-by-wire have not and will not replace humans, but it has fundamentally changed how humans interact with air and spacecraft. These inventions make flight safer, more efficient, and more ambitious than ever before.
All right, guys. Good news. I heard if it's next video, number 6 is good, I get sent to a great place. But if I not good, I get sent to a horrible place, and it's right behind me. Wrong one. Wrong one. This is number 6. Please.
In 1957, the Soviet Union launched the first satellite Sputnik into space, kicking off the space race. 5 years later, in 1962, JFK gave his infamous "We choose to go to the moon" speech.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
When President Kennedy gave that speech, most of the technology required to go to the moon had not yet been developed. So NASA scientists had to spend the rest of that decade developing the new technologies in order to reach the moon. The first of these new technologies was the Apollo Guidance Computer, which was the first computer to use integrated circuits and use a digital fly-by-wire system to eliminate human error when piloting the spacecraft. It was later adapted for use in airplanes, cruise control, and anti-lock brakes. Another development was the fact that they needed to miniaturize the computers enough to fit into the spacecraft. This led to the rapid acceleration in computer technology. Finally, memory foam was created and used in the astronaut seats to reduce the impact of takeoff and landing. The spacecraft that they used to get to the moon was made out of 2 distinct parts. The Saturn V rocket, which was used to shoot them up into space, and the Apollo spacecraft, which was used to get them to the moon. The Saturn V rocket was made up of 3 parts, the first, second, and third stage, all of which were jettisoned once they were no longer needed. The Apollo spacecraft was also made up of 3 parts. The lunar module, which would land on the moon's surface, the service module, which housed the propulsion systems, oxygen, and water, and finally the command module, which housed the astronauts for most of the mission and was the only part to return back to Earth. Finally, there was the launch escape system, which was located at the tip of the rocket and was to be used if anything went wrong during launch.
T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. Liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Roger, tower. Roger, we got a roll program. Flight pilot, pleasure on reporting. Roger. Get your program. Let's put Apollo 11 on a proper heading. Bravo.
One Bravo is a...
Flight line safety almost in the water. Roger, RSO.
Altitude's 2 miles.
Okay. Roger, how you boosted? We're going flight.
Downrange 35 miles, 30 miles high. Standing by for the outboard engine cut down now.
We're going flight.
Station. And ignition.
Cut off ignition. Roger. Trajectory verified. Roger. Thrusters go all engines. Looks good.
11 Houston, thrusters go all engines. You're looking good. Hi, Roger. You're loud and clear, Houston. At 3 minutes, downrange 70 miles, 43 miles high, velocity 9,300 feet per second. Capability. Mode 4.
Mark.
Mode 4 capability. Mode 4 and Apollo 11 could get into orbit using the service propulsion system now. Altitude is 100 miles, downrange 883 miles. Outboard engine.
Engine and ignition. Ignition confirmed, thrusters go.
Ignition confirmed, thrusters go, 11. And we have a good third stage now.
Roger.
30 feet, 2.5 down. Straight shadow. More forward, just into the right level. 30, down a half.
30 seconds.
Forward, just a moment. Good. Right. Contact light. Okay, engine stop. APA at a descent. Auto descent. Auto control both auto descent engine command override off. Engine arm off. Port 13 is in.
We copy you down, Eagle. T1, stand by. T1.
Tranquility base here. The Eagle has landed.
Roger, Tranquility, we copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
That's one small step for man. One giant leap for mankind. As the surface is fine and powdery, I can pick it up loosely with my toe. It does adhere in fine layers, like powdered charcoal, to the sole and sides of my boots. I only go in small fraction of an inch, maybe an eighth of an inch, but I can see the footprint of my boots and the tread, and they fine sandy particles.
The court said that the video is so good, they're letting me out of prison, out of New Jersey. So I'm going back to South Carolina to stay in my new home. That's right, I'm living in this house back here. I saw some guy called John Marlette. Anyway, number 5. I need 100.
The ISS, or International Space Station, is a huge achievement. It was launched on November 20th, 1998, and created by NASA, Roscosmos, JAXA, CSA, and the European Space Agency. Here's the first part of it, which is modules. Here is a Columbus module, an example of one of these entirely unique things. These modules can be used as labs. They can also be used as living quarters, storage, or airlocks. Mainly they're attached by airlocks. And pull up the image, there it is. See, aircraft propels these things up and then they attach them to the ISS, making them modular, a module. Here's an airlock. See, these airlocks are what attach spacecraft and modules. They allow very easy access to whatever's inside. Here's a detailed graph. Look at this very closely. Now, the ISS was created after the Cold War during a period of peace. It was created as a joint project, a way to ease tensions, and therefore this is a symbol of cooperation in this new era. Now, back to the modules. Get a look at the size. These modules are pretty hefty. Sometimes they're even equipped with little attachments on them, such as wings, solar panels, or whatever they needed. Modules come in all different shapes and sizes, as seen like here. They can also have different attachments serving different purposes. The ISS also comes equipped with solar panels. This is very handy because, well, in space, in the sun. This is an excellent way to get energy, as the size will capture a lot of energy, which is needed for the sheer mass and size of the station, as well as to power all the different technology that is inside. The ISS is around 365 feet, 109 meters long, and about 240 to 360 feet, or 73 to 109 meters wide, with the mass of nearly 1,000,000 pounds. And it's made out of aluminum alloys, stainless steel, and titanium, which make it strong resistance. Because in space, well, you're obviously gonna have debris, asteroids, stuff like that hitting you. So you have to make it strong. Here are more arrays, as you want to collect as much energy to power tons of advanced technology, which is mostly located in labs. Now, here is the integrated truss system. It is an advanced system that makes it strong, because trusses are a very strong design. Here is the full length of it. It allows for modularity and strength. Here is a blown up picture showing sections. They connect together to form a strong system. Now it's time for a media break. I can see the other clip. We know how it was originally built by attachment modules into sections like this here. But here's a very important question. What does this mean for our future? This could allow us to have cargo transport over however long distances. We could maybe live in space using these technologies. Some technologies that are used are water purification systems, such as electrolysis, which break down water.
That was so much fun. I think I have to sing.
Fortnite, let's go. I get it all night for sure. I'm on a Fortnite, let's go. I get it all night for sure. Yeah.
That was so good. Anyways, next we have number 4 by Sergeant. I don't know how to say his last name.
Ladies and gentlemen, your General, Angela Dorazio.
Everyone shut up! Listen, today is very important. Today, we're learning about how we're going to turn the tide in this war.
What did the cow say to the guy blocking the way?
The engineers have been cooking. And they call it Antonio, shut up. Shut up. They call it the B-2 bomber. Okay? So here's the deal. Your normal plane, 4 parts. And it looks like this. You got the tail, got the empennage, got the wings, fuselage, and if you want to count the cockpit, you got 5 parts. Not our plane. Our plane looks a little bit more like this. Like that. 1 part. Wing. Listen. The B-2 bomber went against normality when it comes to its design. Lacking a fuselage, an empennage, and even a tail, the B-2 is essentially one giant wing. 1 wing. This drastically reduces the radar cross-section of the aircraft, making it extremely hard to find with typical radar systems. As a matter of fact, it is 1,000 times harder to spot on a radar screen than a B-52. Additionally, it makes the aircraft extremely aerodynamic, increasing fuel efficiency and longevity of flight. This is absolutely crucial for the B-2, as it may have to fly halfway around the globe and back just to dump its load and bomb a country. The B-2 also has very minimal seams and lines in its design. This is because any edge can potentially reflect radar. The shape of the aircraft is far from the most impressive innovation that the Americans made for our bomber fleet. The B-2 is coated in a classified, top-secret material that actually absorbs radar instead of reflecting it. While the exact material is not publicized, people have inferred that it uses ferromagnetic materials, which are materials, in case you idiots didn't know, are prone to magnetization, that absorb radar and create fiction, which in turn is dispersed as heat. This may be the biggest scientific advancement seen in the B-2, as the secret material put the U.S. ahead in the stealth department. It also causes civilians to try to replicate it and use it for things like street racing to avoid speed traps. While aerodynamics and radar dodging are all daunting challenges, the real obstacle lies in the issue of stabilization. We just went over 5 parts of a plane. This has 1 part, and guess what? Without some crazy tech, it's going to do a whole lot of that. Explode, crash, everyone's dead. So, our engineers cooked up again. The last major innovation lies within the engine system of the B-2 and the stabilization. So, without horizontal and vertical stabilizers, it's going to sway back and forth. So what they did, they developed a very advanced fly-by-wire system that uses computer systems to sense and adjust surfaces on the plane on the fly, which not only stabilizes the aircraft, but allows for crazy maneuvers people didn't think were possible for a plane this size. As for the engines are hidden deep within the wings of the B-2. This reduces sound and more radar reduction. Additionally, the exhaust is cooled and distributed broadly all across its big backside. All right, all across that big backside. What that does is reduces the infrared signature of the plane. What we're going to do is we're going to show the Soviets how we rock. Because these Soviets, they got a crazy defense system. Right now, not going to lie, we're a little cooked. But with this puppy, we won't be cooked. Our main issue is we are trying to infiltrate their radar systems. Get in and get out. We want to spread our seed, the need for speed. We don't even want them to know. That's what this addresses right here. Any questions? Class is dismissed. Now get out of here.
That was a beautiful presentation. And I'm not just saying that because he can crack me in half like a glow stick, but I'm saying because he's a true American. Godspeed. Our last read for number 3. We have the Raptor.
This is the F-22A Raptor for the 1.1.1 presentation on aerospace advancements. The Raptor had its first flight on September 7th, 1997. Lockheed Martin had begun the project in the late 80s. It entered operational service December 2005. It was made by the Skunk Division. That division worked on the SR-72, the F-117, I think the F-35, not sure on that. And these are the engineers that worked on it. They weren't associated with Skunk Works. They don't really tell us who was involved with Skunk Works. In the early 90s, air combat doctrine was moving away from the gunfight and short-range IR missiles, and they learned that they needed a supersonic stealth craft that could lock targets at long range with less danger to itself, and they fulfilled that request in 1997. The F-22A Raptor enters operational service in December 2005, boasting twin Pratt & Whitney F119 PW100 turbofan afterburning jet engines, rocketing the craft to a maximum speed of 2.25 Mach at altitude, as well as Mach 1.76 supercruise, and giving it 460 nautical miles of combat range. And that could be extended if they don't. That's holding a combat load and supercruising. They can, if fully empty and using less fuel, they can go about 1,000 nautical miles. It uses the NACA 6 series airfoil to prioritize laminar flow over the wing and maximize fuel efficiency. They really like that on their late 90s stealth craft, combining the principles of angular shaping to bounce radar beams off and prevent the beam from responding to the receiver. They also used this special paint that coated the craft to block radar. Because, the way the radar works, it sends out a sound signal, bounces off something, comes back to receiver. So the idea is to use specific paints and rivets and whatevers to make the beam bounce in a different direction so it never returns to the receiving craft. Proving itself the dominant force of the skies, it brandishes a 20mm M61A2 Vulcan rotary cannon with 480 rounds, and in armament choices including but not limited to the AIM-120C AMRAAM, the AIM-9MX Sidewinder, JDAMs, JB-39s, or just drop tanks. It also holds an AN/APG-77 ASIM radar. It can detect targets that are at least 1 square meter in size, about 150 miles out. Also equipped with MLDs, IRSTs, electronic weapons pods, and integrated CNI avionics. All these things come together to make a hypermaneuverable, supersonic, interdiction, and air dominance craft that's capable of, in a pinch, acting as an air-to-ground, but generally allowing the Air Force to secure a large area and control it, and not really see much of a threat from late 90s Soviet surface-to-air missiles. And here we got some pictures. This is a stealth coating. Whoever took this picture was noticing the scratches here, but you can see it popping in there, the difference between the coating and the base steel. This is the AIM-120 AMRAAM, and there are just some blueprints there. This is what the news was saying around that time. There's a lot of cynics with this. It seems around the time most people were worried about the cost of it, but they always are. You got this guy saying over the top gun, and throughout that article, he's just being mad about how much it costs. America's spirit. This one, was I the only one saddened at seeing Spirit of America blaze on the side of the Raptor, characterized as carrying a heavier. Yeah, this dude's mad that the Spirit of America is a big bomb, but it sucks to suck. World events around the time. Berlin Wall falls in 1989. The first Iraq War begins in 1991. The DHKPC insurgency begins in Turkey in 1990. The Somali Civil War, the Iraqi uprisings, the Soviet coup, and the 1998 U.S. Embassy bombings. And this is all shaping out to create a new decade of air combat. You're seeing the Soviets being forced to mobilize away from traditional Soviet air doctrine, pulling away from high-speed air interdiction over into actual fighter combat. And we're also seeing with the Iraq War and seeing that America is now further in the Middle East, is that surface air missiles and air guns are a lot bigger of a threat than other air threats. So we learned that the need for the fighters to be able to get in, secure an airspace, or accomplish a target and not be picked up by a surface-to-air missile. How do we get here? The Hav Blue and the F-117 Nighthawk projects. So the Air Force realizes that the fighter must be invisible to radar to survive the increasingly lethal Soviet surface-to-air missiles. Again, that's coming from the Middle East, where in the Iraq War and Afghanistan War, there wasn't really a big MiG threat. What the threat was Taliban surface-to-air missile sites up in the mountains. So they need something that won't get picked up by surface-to-air radar from way too far away. The Pratt & Whitney F-119 engine allowed the jet to fly at supersonic speeds without using its afterburner, increasing the range and making the jet harder to track via heat-seeking sensors. And that's just creating our hypermaneuverable fighter. Really gives it that edge in close-range combat that you won't see that much. ASA and EW improvements, allowing the radar, electronic warfare, and communication systems to talk with each other, presenting a single clear picture to the pilot rather than a mess of raw data. That's a lot of the problem the F-35 has. It doesn't matter quite as much how much information you can give to a pilot, but how easy it is for them to interpret it. The F-22 does a really good job of giving you one solid, clear picture of what's going on and not overloading the pilot with information. What now? So the ability to supercruise at Mach 1.5 without an afterburner, it really propels engine spaces in modern fighter craft. After the F-22 comes out, you see the Chinese, I believe they had the J17 or J35, something like that. And you see similar appearances in engines. You're seeing a lot of hyper-maneuverable fighters. In the Su-57, it's a lot more better at hyper-maneuverability than it is stealth. Thrust vectoring, the F-22 uses 2D nozzles to direct its engine thrust, allowing it to perform post-stall maneuvers, moving the nose in directions the plane is not traveling, which allows larger craft to become hyper-maneuverable, pushing the boundaries of fly-by-wire software, as computers must now manage flight surfaces and engine nozzles simultaneously. Fly-by-wire is using a computer to make flying a craft a lot easier. It started, I believe, in the F-16, where the F-16 was unstable, so they had to use a computer to automatically adjust trim and flaps and stuff, keep it level. And doing that, allowing the computer to focus on keeping flight stable and level and where it should be, lets the pilot focus on making maneuvers and telling it what to do. It takes a lot of the burden off your pilot off. Radar observant material, RAM. The F-22 uses a specialized coating converting radar waves into heat. Advancements here lead to the more durable stealth skin on the F-35. I mean, that's pretty self-explanatory. The MOSA approach. Recent F-22 upgrades have moved away from the locked proprietary software to open architecture systems, allowing for plug-and-play updates where new sensors or AI can be added in weeks rather than years. That's just the Air Force trying to move in to make it easier to retrofit their aircraft so they don't have to roll out a new set of block aircraft every 5 years. And here's my works cited. All right, 90.
Nice PowerPoint presentation, nerd. I got the nerd, am I right?
Oh, brother, this guy stinks!
Anyways, for number two, one away from the final one. Number 2 is going to be the Mars rover.
Alright, so the Mars rovers, we all know them. They're really cool robots that travel the surface of Mars, and they study its geology and search for signs of water and life. The very first rover attempts were the failed Mars 2 and 3 missions by the Soviet space program, headed by Alexander Khamarjan. In 1971, at the end of the space race, they launched 2 small rovers called the Prop-Ms. The first crashed and the other landed but lost contact with Earth seconds later. They used skis rather than wheels and were only about the size of a textbook. They were kept a secret for decades, and our knowledge of them only came to light after the fall of the Soviet Union in the 90s. More than 2 decades later, Sojourner was the first rover to successfully land on Mars. Its team was led by Tony Speer of NASA's Jet Propulsion Laboratory, the department which would go on to be in charge of all the American rovers. It landed in July 1997 and was a sensation on Earth. It was built during the renewed interest in space in the 90s, in a similar time frame as the Hubble Space Telescope and the ISS, and it was also landing right around when the internet was taking off, and it got so much attention that it broke the internet. NASA's servers just couldn't handle the millions of people that were watching for live updates and images from the rover. It did stop functioning in 1998, but not before laying the groundwork for the next generations of Mars exploration. Led by Peter Thesiger and landing in 2004, Spirit and Opportunity were matching rovers with the goal of looking for evidence of water on Mars. They succeeded this mission and exceeded their planned 90-day lifespans by years. Not only did they find strong evidence of ancient liquid water on Mars, Spirit lasted for 6 years and Opportunity 15. With this knowledge that there was water, and thus potentially life, Spirit and Oppie inspired the next Mars missions. The Curiosity rover landed in August 2012, its team headed by Ashwin Vasavada. The goal of the Curiosity was to determine if it was possible that Mars could have supported life. It is still functioning today, a decade after its planned 2-year lifespan. Since it found that it was possible for life to exist on Mars, Perseverance was the next step that looked for evidence of life on Mars. It landed in February 2021, led by Jessica Samuels. Perseverance's mission was to find signs of ancient microbial life on Mars, but it also collects rock samples that are meant to eventually be picked up and studied by scientists on Earth, and is testing technologies that could potentially let humans live on Mars. It also held a drone called Ingenuity, which tested if flight was possible in Mars's thin atmosphere. Percy is still working today. The latest rover, Zhurong, was made by the China National Space Administration and led by Zhang Rongqiao. It landed in May 2021 with the mission of studying the geology of Mars and ice on its surface and analyzing its atmospheric conditions. While it unfortunately shut down in 2022 due to dust covering its solar panels, it lasted more than twice its planned 90 days. It took a lot of scientific advancements to make the rovers a possibility. We needed rockets that could make it all the way to Mars, unmanned spacecraft, heat shields, solar panels, EDL, or entry, descent, landing technology like specifically designed airbags and small maneuverable rockets, among much more. The Viking landers from the 70s, for example, were the initial successful Mars landers that paved the groundwork for future Mars missions. They also inspired Curiosity's and Perseverance's sky cranes, a crazy landing system that was so high risk and uncertain that the scientists called Percy's landing sequence the 7 minutes of terror. But those risks were worth it, however, as not only do we have so much more knowledge about Mars, the rovers led to a lot of aerospace advancements. New airbag systems were developed for Sojourner, Spirit, and Oppie's landings, and Perseverance is currently testing life-sustaining technologies, including MOXIE, which converts the Mars atmosphere into breathable oxygen. In addition, because of the minutes-long communications delay between Earth and Mars, it was crucial that autonomous navigation systems were developed. As for future developments, NASA is currently working on a way to collect Perseverance's rock samples. Eventually, the research and developments of the rovers may be used to sustain human life on Mars. In short, the rovers were awesome, they were complicated and took a massive amount of time to create, and that effort was well worth it for all the knowledge that they have given us. They're super sick, and I don't know how to end this. Bye.
All right, and now last but not least, for number 1, we have the Scramjet.
It's hard. Oh, we're live, sir.
What about today? Why is everyone mad at the plane? It's so much altitude. Hi everyone. Welcome back to Learning with Antoine. And today, we have quite an exciting segment. It's about scramjets. Everyone loves them. I don't know them. And you don't either. That's why we're here to learn. So, essentially, scramjets are just short for supersonic combustion ramjet, with the concept originally being conceived during the Cold War times. Because, let's be honest, US, Soviet Union, they didn't cram well. So, let's scram well. Essentially, they were trying to create a super fast way to create flight for military use, and just for basically showing, oh, we're better than the other team. So this led to huge technological advances, which led to the theory being conceived of scramjets. Supersonic flight. Who doesn't love that? I sure do. Actually, it's hypersonic flight. Had a blank there. So now, let's fast forward a bit to 2000s, where NASA created an X-43A, setting a record for Mach 10 flight. That's kind of fast. Not as fast as me though. I'm faster. Since then, multiple experimental flights have been created, along with, of course, the 43A, Boeing's X-51, and DARPA's Hawk, like Hawk 2, which shows hypersonic flight. All right, walk with me here. Essentially, these jets all perform above Mach 4.5. That's pretty fast. Not as fast as me again. But essentially, I got my little buddy here, Latios here. He's a Pokemon, not a jet, but he's modeled after a jet, so it works. So essentially, going supersonic speed means around you supersonic air. Essentially, takes that, compresses it into the engine, allowing for the thrust to just straight up let it take off. Going, again, above Mach 4.5, achieving hypersonic flight. And not only that, but thanks to the air compression, the machinery, all used inside the big airplanes or the commercial airplanes, not needed. It's lighter, it's faster, it's better. Like me. It's not a need for an oxidizer or any other useless machinery you see in those boring planes. Blech. I know, right? It's pretty boring. So essentially, we went over what they are, how they work. You know, scramjets aren't that common. With more and more technological advances being made in our society, more and more ways for it to be commercialized. Just think of that. That was Learning with Antoine. Have a great day, everybody. Yeah. Hey guys, there was some information I missed out. I take accountability here. We're here to clarify. Some more planes here, like the Australian High Shot series. They were early test flights though. So, and then Russia's I'm not Russian, I can't pronounce that. Daniel, you got that. There's also, especially recently, there was a major development that with India that forced
mountains, India again, I guess, and China to create advanced hypersonic weapons with the technology obtained from scramjets. Cool stuff. They also, again, since they use air for combustion at supersonic speeds, they also made a range of pod designs for the engine systems, which are all 3D engine geometries, or the applications are. Sorry. And this also applies to the SR-71 Blackbird's unique engine system, so it can, of course, go supersonic speeds. And yeah, there's multiple different generations of pod style paneling, with the first gen, second gen being the second gen incorporated with the aircraft body, the first gen being the external compression, and then the third gen is the one with 3D geometries. And yeah, that's about it. I think my dance is after this segment. And yeah, don't mind the paint. That's for my... Don't mind the paint, that's for my room. Because we're playing the paint soon. Have a good day.
Alright guys, and that was the last video out of the evolution of aerospace from 1903 to present day. Hope you guys liked that video and learned something. And remember to subscribe, like, and ring that bell for notifications. And Marlek fam, I will see you later. I can't find the gift. Peace. We would end this video without some shout-outs for the credits for everybody who made the videos. We're shouting out first video, Janky, Tayson, Eden, sorry, pipe. Janky did the hot air balloon, Tayson with cabin preservation, Eden with the radar, Xavier with jet engine, me did the supersonic flight, Canuck did aerial refueling, Christian did helicopters, Daniel did the tracking missile, Nick did the fly-by-wire, Apollo 11 with the My Rudy, Aiden did the ISS, Angelo did the B-2 bomber, Lucas did the F-22 Raptor, Max did the Mars rover, and Antonio embarrassed himself and did the scramjet. Russell, and the goated teacher, Mr. Marlette. Let me go big fat kiss. Marlette, or